Hi, we're Group 17. Our project is Lookout Tower utilizing CNNs to detect wildfires. I'm Jordan High.
And I'm Will Wright.
And I'm Llewellyn Johnston.
So the motivation for our project is due to the recent wildfire devastation in the news, both in Los Angeles and in North Carolina. An earlier detection of wildfires can help limit damage and allow emergency responders to perform more efficiently. And our project aims to develop a convolutional neural network that can effectively detect wildfires in remote areas and hopefully become a valuable tool for responders across the globe. Our model methodology and metrics, the input is just several images of various ecological areas, either undergoing a wildfire or just in a natural state. And the output is either a classification of either a wildfire that's in progress or a safe area with no fire, and that's binary classification. As you can see from the histogram of our Kaggle dataset, there's a slight imbalance between our no fire and fire classes, and this problem was mainly handled through a class weighted loss function that had a heavier weight towards the fire class, which penalized the model more when it misclassifies a fire. We also use data augmentation and transfer learning, which will be mentioned later on. And for the metrics, we primarily used accuracy to get a strong overall performance indicator. Precision will tell us how often we get a false alarm in the model. Recall will be one of the most important metrics because it's going to show the model sensitivity to wildfire indicators, and it will tell us if it actually catches most wildfire cases. Finally, F1 score is also measured to reassure reliable performance as it is a mean of precision and recall.
Yeah, so getting into our actual model architecture, the big part of our model, then that was an improvement on our base, was that we moved over to using a convolutional neural network, and we utilized some transfer learning from a pre-trained model called ResNet 18. So the process going through our model was that we would process all the images coming in, we would resize them to 312 by 312 pixels, enhance the image contrast, and then apply an edge detection and overlay that on the original image, just so that when the model looked at the images, it had a bit of a more stark edge. Then from those images, we'd pass them into the pre-trained ResNet 18 convolutional layers that would extract out 512 features, each being a 1 by 1. And then from those 512, we'd pass it into a two-layer MLP, where we would take those 512 attributes, we'd compress them down to 256, and then from 256, we'd compress them down again to our two-state binary classification of fire or no fire. Then going on to our training approach, we initially started with a pre-processing of the images and then passed it into our model. As one issue we ran into is that we had lots of problems with our data set being quite small, so we approached it with a k-fold split. We initiated with a 10 k-fold split, then applied some image distortion to try avoid overfitting to our model, and we specifically used horizontal flipping, rotation, and color jittering on that data.
Thanks, Long. So as mentioned in our last presentation, our baseline model consisted of a random forest model with little pre-processing of our data, our new model with the ResNet 18 pre-trained model, and our two-layer MLP architecture. We got some pretty good results from that initial model from the new architecture. We initially shifted to just using a pre-trained model, which was the ResNet 18, through transfer learning to perform out some convolutional steps, which immediately gave us excellent performance improvements. As you can see, the lowest performance increase was our precision, but about 6% increase. But we saw the model overfitting a bit to our training data, and we were struggling to generalize to a great extent as well in the test set due to our relatively small training data set. So as you can see, to address those issues with the small training data size and overfitting, we added the k-fold split, as Will mentioned earlier. We introduced that to the model and some data augmentation as well during the training, like tilting, mirroring, and color jittering. And this allowed us to push our model in pretty much every aspect to what is generally considered excellent performance by industry standards, with all metrics improving by at least 11%, with the greatest being about 15.6% with the recall, which is very good for us considering that was our most important parameter in terms of sensitivity to fires in our model. So going into a little bit about further improvements, these are the misclassified no fire images from our test set. And as you can see, we're still having some visual patterns that are confusing the model. So natural fog, mist, and clouds still remains to be a big challenge when it comes to this sort of problem, as well as warm colored lighting. triggering false fire predictions, and atmospheric haze and overexposure. As you can see, kind of the fog in most of these pictures on the top, and the red hue in some of these bottom and middle pictures. In terms of fire misclassification, mainly we're seeing smoke again still being a problem, as well as low background contrast and a lack of clear fire indicators. Only getting subtle indicators like a red hue, as you can see in this bottom image, as well as on the right, where you see like the fire on the side, but more of a natural setting on the left, and this middle one as well. It's mainly when the smoke is very thinly spread throughout the image. So in terms of further improvements and what we can further potentially think about pushing this model in future studies, potentially shifting to a video contextual model. So fire behavior is more dynamic, so maybe a video can help get better context for the model information, as well as introducing some sort of atmospheric data to the model or attention layers to help shift focus away from misleading parts of the image, as mentioned earlier. So yeah, that pretty much remains the project. So in terms of prior work, as mentioned previously, me and Jordan don't have any experience in CNNs aside from this class, and Llewellyn has a little bit of experience in machine learning. But regardless of that, nothing else otherwise in this class. And then our references are our data set from Kaggle and GitHub Copilot for helping in code development.